This lesson deals with supplemental problem 413. You can find this problem in the ECE302 ebook in the Chapter 4 Supplemental Problems, starting on page 24. The circuit shown below is a MOSFET H-bridge motor reversal circuit and was a magazine article in Popular Electronics in volume 16, number 7, entitled Voltage Reversal Circuits Plus by Charles Rakes. Suppose that for these transistors, we have a threshold of 3 volts and a K of 1.25 amps per volt squared for the P-channel devices, and for the N-channel device, which is 750 milliamps per volt squared. Let's use the motor that we used in the previous chapter with a resistance of 25 ohms and an inductance of 10 millihenries. I'd like you to find the voltage across and the current through the motor if S1 is closed and S2 is open at t equals 0 seconds. Then if S1 is open and S2 is remaining open at t equals 60 seconds. Then could you repeat A for S1 open and S2 closed, and repeat B where both switches are open. In our first task, S2 is open and S1 is closed. Let me go to the previous page and let's do this part here right on the drawing. Back on page 24, we've now got the switch S1 closed and I've got S2 open. Open this switch, there'll be no chance for getting any current or any voltage across here. That's going to give me a gate to source voltage of 0. That's going to make this an open circuit or cutoff. With this switch closed, I've got 5 volts across the gate source. We're either in the current saturation region or in the ohmic region. Because this is a switching circuit, I'm going to guess that this is in the ohmic region. If this is in the ohmic region, this voltage across here is approximately 0 volts. It's like a short circuit. That's going to put a voltage here of 0. Back up over here, the source to gate voltage for M1 is going to be 5 volts minus approximately 0. This is about 5 volts. This implies that we are either in current saturation or in the ohmic region. And again, I'll guess it's the ohmic region. And again, the voltage across here would be approximately 0 volts when the current flows through because it's a very low resistance. Now that makes this node voltage here 5 volts, and that's hooked up back over here. I've got 5 volts here, and I've got 5 volts roughly here, so this is approximately 0 volts. That makes this transistor cut off. I have a path for current, come out of here, go through here, come back and go back around the power supply. Let's check whether our guesses were correct or not. Let's find the drain, the gate voltage for transistor 1. Drain, and here's the gate. Here's the drain, and it's sitting at 0 volts here, roughly 5 volts, and this is sitting at 0 volts. Got 5 volts across here. That does check that that's in the ohmic region. They're both greater than threshold, given that the threshold was 3 volts. Take a look at transistor 3. Let's find its gate to drain voltage. This is 0 volts, and this is sitting at minus 0 plus 5. 0 minus 5 is minus 5. Of course, that's less than threshold. This is cut off. Let's do transistor 2. Here is the drain, and here is the gate. The drain's sitting at 0 volts, and the gate's sitting at approximately 5 volts. We got minus 5 volts across here. Both less than threshold, which was 3 volts, and this is cut off. And then lastly, let's find the gate to drain of transistor 4. The gate's sitting at 5 volts, the drain's sitting at 0. We've got 5 volts across here. The gate to source and the gate to drain are both greater than threshold of 3 volts, and so that would put this in the ohmic region. Guesses were correct, and again, the path for current is going to be through here, back to ground, back up to the power supply. Now let's go back to page 25. And this is what we just did. Our assumptions check. I've redrawn the circuit with the transistors that were cut off, just erased. There was one here and there was one over here. I replaced the motor by its model of 25 ohms and 10 millihenries. I want to solve for the current through it and the voltage across it. Let's calculate the resistances of these MOSFETs that are in the ohmic region. In supplemental problem 412, we had a formula for the resistance, and for the P-channel device, it went over 2K, quantity, source to gate voltage minus threshold voltage. K is 1.25 amps per volt squared. The source to gate is 5 volts, and our threshold is 3. We get a pretty small resistance, about 0.2 ohms. Then for transistor 4, same formula, but the subscripts are reversed here. With the gate to source voltage, K was equal to 750 milliamps per volt squared. Gate source was 5, threshold was 3, and that's giving me 0.333 ohms. I've got a circuit that's got a battery in it, a resistor, and then one inductor. So we have a first order differential equation. Like we had said in ECE302m, the formula solution is sum A plus B times e to the minus t over tau if we're starting at t equals 0. Tau is the time constant, and that's the inductance over the resistance seen by the inductance with all the independent sources set equal to 0. We short this, set it equal to 0, and look back from these terminals of the inductor. What do we see? We see 25 ohms in series with 0.2 ohms back to ground. And then on this side, we see a resistance back to ground of 0.333. And that's what we have right over here. That gives me a time constant of about 400 microseconds and 392 microseconds to be more precise. The current flowing through the motor or the inductor prior to us starting the problem was 0. We had everything shut off. And then we applied power and closed the appropriate switch. The current that was flowing in the inductor is the same before and after that switching event. Can't change instantaneously. And that was equal to 0. And that's going to be our formula, A plus B times e to the minus 0, but e to the 0 is 1. If we wait long enough, eventually this inductor will look like a short circuit. We can analyze the circuit with a short circuit present here. The current that's flowing in here is going to be the current in the resistances. That's going to be the 5 volts on top. I've got a resistance here of 0.2, 25, short, and then I've got 0.333 ohms. The value of the current as we approach infinity is 5 volts divided by these 3 resistances, and that's 196 milliamps. That's going to be my equation, A plus B times e to the minus infinity over tau, and e to the minus infinity is 0. It's the value of A. The solution is going to be A, which is 196 milliamps, and then B over here is going to be equal to the negative of A minus 196 milliamps times e to the minus t over tau, which was 392 microseconds. This will be true for t greater than or equal to 0. Note here, 5 time constants is only 2 milliseconds. This equation is going to happen very quickly. We're going to go from 0 current to 196 milliamps. What's the voltage across the motor? Go back into our schematic. Take this short circuit off of here. Voltage across the motor is going to be this node voltage minus this node voltage. And this node voltage here is going to be minus the drop across here, so minus the resistance of 0.2 times the current in the inductor, plus 5, and then minus this node voltage, which is going to be the current in the inductor times 0.333. And that's this equation on the next page. We've got minus 0.2 times that inductor current, and then minus 0.333 times that inductor current. Let's put in our equation for I sub m, that's over here, 196 milliamps times this quantity. The product of these two is 0.104. This equation is going to go very quickly 5 volts. We're subtracting a very small number from here, so it's approximately 5 volts. We've got a constant voltage across the motor, and the motor will start to spin in a particular direction. At t equals 60 seconds, we're now going to open switch S1 and keep S2 still open. Our equation for the inductor had a time constant of about 400 microseconds, and 5 times that is much less than 60 seconds. We've reached the steady state value of that inductor current of 196 milliamps. Let me do the following things here on the drawing. Might be a little bit easier to see. I've got a motor with a model, and I've got a current flowing through it just before we flip the switch, and now after we flip the switch, this is still the same value of 196 milliamps. With this switch open over here, there's no current coming in, 0 volts here. That's going to cut off the transistor, M3. And with this switch open here now, likewise no current can flow, and I've got no voltage here, and this is also cut off. I've got no current in the drain, the source of these two transistors. I tried a lot of different combinations, but the only one that would work for current to flow, and I've got to get this current to flow, is to actually come through the diode that's between the bulk and the drain of transistor 3. Suppose that current goes through here, comes through here, and then goes back through this transistor back to ground. Let me see if I can prove that that's true. With this forward bias in this direction, this node voltage is a minus 0.7. And that makes this source to gate voltage here 5 volts minus a minus 0.7. So this is 5.7. This again keeps this in ohmic, and the current can actually flow in this direction in the third quadrant, as we've shown in the notes in chapter 4 on page 9. That's going to create a negative voltage across the source to drain. That's okay, you can operate in that third quadrant. How about this transistor over here? If this transistor is an ohmic, then this node voltage here is going to be a very small value of resistance times this current plus 5. So this is about 5 volts, and the voltage here is 5. This is going to be 5 volts minus a number that's maybe a little bit bigger than 5, about 0 volts here. I'm going to make this below threshold. This is also going to be cut off. That is a cutoff, and cutoff transistor, one that's in the ohmic region, and my path for current is going to go back through here. Rather strange, but that can happen. Let's see if we can solve some of the equations for the voltage across and the current through the motor. As we said, M2 is in the ohmic region. Let's use our formula for the resistance, which was twice K, which is 1.25 amps per volt squared times 2. And then the source to gate voltage was around 5.7, and the threshold's 3. That's going to give me a very small resistance, in this case 0.148. Let's go back to the previous page. So I've got a circuit, the battery, a resistance, another resistance, and here's a battery in a sense, and then one inductor. So a first order differential equation. This one's going to start at 60 seconds. You write that as some new A plus B times e to the minus quantity t minus 60 seconds over tau. And this would be true for t greater than 60 seconds. What's the resistance seen by the inductor? Let's go previous page. So looking back into these terminals, what do I see? With all the independent sources set equal to 0. This is a battery, in a sense. It's minus 0.7. We've got a short here back to ground. See from here back to ground 25 ohms, and then this is shorted back to ground. From here I see the ohmic resistance, which is 0.148. Let's put those two together, form our time constant, which is now about 398 microseconds. Our current just before we did the switching was 196 milliamps. It must still be there, and that's going to be this equation evaluated at t equals 60 seconds plus, and that's going to be e to the 0, so we get a plus b is equal to now 196 milliamps. What happens as t approaches infinity? Well, the circuit doesn't know this, but eventually the motor is going to shut off as we pass through 0, so there won't be a path for current. We can solve this equation pretending that everything's going to be here and we're going to short this inductor. If you were to short this, the current that's flowing is going to be the voltage across the total resistance divided by the resistance. This node voltage is minus 0.7 and this node voltage is 5. The difference of those two, minus 0.7 minus a plus 5 is a minus 5.7, and that's across 25 ohms plus 0.148. And that's a minus 227 milliamps. That's going to be our equation as t approaches infinity, the a plus b times e to the minus infinity, which is equal to 0. So just get a, and we can solve for b. B is going to be equal to 196 milliamps minus the value of a, but a was a negative number, so plus 227 milli, and that gives me 423 milliamps. My equation now for the current in the inductor is a plus b times e to the minus quantity divided by tau. And this equation is true for t greater than 60 seconds. This equation will eventually pass through 0, and when it does, the motor will shut off. And let me show you why on the drawing. Previous page. Current is flowing through here. It's decreasing. Eventually it's going to change direction and try to go in the other direction. But if it tries to go in the other direction, it could go through here, it could go through here, but this is cut off and this is cut off, and there's no path for current. The motor will just shut off at that instant in time. Let's go back to our equation then. Let's figure out how fast that's going to happen. We can take this equation for the current in the inductor of our motor and set it equal to 0 at some time t1, and then solve for t1. I'll bring this on the other side of the equation. I'm going to divide this over here, and that ratio is 1.86, and I'll take the reciprocal of this to get a plus sign here, and then take the natural log of both sides of the equation. So I just get the argument, t1 minus 60 seconds over the time constant, 398 microseconds, equals the natural log of 1.86. Cross multiply by this, and then I get the difference of these times is 398 micro times the natural log of 1.86. That's equal to 247 microseconds. This equation is true for t greater than 60 seconds, but it only is true up to 247 microseconds added to that. Well, that's the same equation, but it's only valid in this small section in time. Now let's figure out what the voltage across the motor is during all of this. Let's again go back to the previous page. The voltage across the motor is going to be this node voltage minus this node voltage. This node voltage is minus 0.7, and this node voltage here is going to be the current flowing through here, through the resistance of 0.148 ohms, and then plus 5 volts. Let's go back to that. This is a pretty small number. We're multiplying that times another small number, so this is roughly minus 5.7. What's happening now is the voltage across the motor has reversed direction because the motor is generating energy. We had stored energy in the inductor through the momentum of the spinning of the motor. And now it's dumping that energy. It's going to dump it pretty fast. It's going to be pretty much all done in 247 microseconds. And then beyond that, we just have no current flowing through the motor and no voltage across it, and the thing shuts off. We're going to start over again. This time we're going to open switch S1 and close switch S2. Let me do all of this on the drawing on page 24. Let me erase this so that we can start over. We're going to close this switch and open this switch. With this switch open, I've got no path for current to flow, and so the voltage across here is 0. That's going to put this transistor into cutoff. With this one closed, I've got 5 volts across here. With a gate source of 5, which is greater than threshold, this transistor can be in current saturation or in the ohmic. Again, let's guess ohmic because this is a switching circuit. The voltage across here is going to be approximately 0. With this voltage being 0, we can go back over here now and we can find the source to gate voltage. It's going to be 5 volts minus this node voltage, which is roughly 0, about 5 volts. This transistor is either in saturation or in ohmic. Again, let's guess ohmic. The voltage across here would then be a very small number because of the low resistance. Let's find the source to gate voltage here. So the source is 5. The gate is hooked up to here, and this is back to 5 volts. It's going to be 5 minus 5, roughly 0 volts. I'm going to cut off this transistor. And now I have a path for current. Current could flow through here, back around. I have to check that those assumptions are correct. But if it is, then the current's going through the motor in the opposite direction, and the motor's going to spin in the opposite direction of what we did in our first part of the problem. Let's check to see whether these transistors are consistent with the guesses we just made. Let's find the drain to gate voltage for transistor 2. This is sitting at minus 0 plus 5, and then this side's sitting at 0 volt. At 5 volts across here. The source to gate and the drain to gate are both greater than thresholds. We're in the ohmic region. Look at transistor 4. Let's find the gate to drain voltage. The gate is 0, and the drain is sitting at minus 0 plus 5, minus 5 volts. We're definitely in cutoff. Both are less than threshold. Let's find this transistor. Let's find the drain to gate. This is sitting at 0 volts, and this is sitting at 5 volts. So we're going to get minus 5 volts again. Both are less than threshold. That's in cutoff. And then lastly, transistor 3. Let's find the gate to drain. Gate's sitting at 5. The drain's sitting at 0. It's got 5 volts across here. So we are in the ohmic region. Let's go back to page 28. We've now done all the things that are here. Our assumption checks. I've redrawn the circuit with the transistors that are cut off erased. I've got transistor M2 and M3 in ohmic. I've got the same model for the motor, but now my current's going in the opposite direction, and the voltage likewise is in the opposite direction. I'll solve for it this way, and we can just note the differences. Let's find the ohmic resistance of transistors 2 and 3. This being a P channel, it's going to be the source to gate voltage, which was 5 volts. K was 1.25 amps per volt squared, and a threshold of 3. That gives me 0.2 ohms, as it did before. And now for this transistor, the N channel, we're going to get a gate to source voltage of 5, a K of 750 milliamps per volt squared, and a threshold of 3. I get 0.333 ohms. I have a circuit that has one inductor, one battery, 1, 2, and 3 resistances. So a first order differential equation. We'll now just say this is at t equals 0. Some new A plus B times e to the minus t over tau. Tau is the inductance divided by the Thevenin resistance seen by the inductance. Let's look through here. With all the independent sources set equal to 0, we're going to set this equal to 0, short that. Looking into this terminal, I see 25 ohms plus 0.333. In this terminal, I see 0.2 plus 0. Taking 10 millihenries, dividing it by the sum of the resistances of the two ohmic transistors plus the 25 ohms, and we again get 392 microseconds. The current that was flowing in our motor prior to this switching was 0, so it must still be 0, and so our equation evaluated at t equals 0 is going to be A plus B. If we wait long enough, the inductor will be a short circuit, and we can find the current in that short circuit by taking the voltage that we have and dividing it across the resistances of 0.2, here's 0, 25, and 0.333. And that's the same as it was before, 196 milliamps. That's going to be A plus B times e to the minus infinity, or just A. Our equation is A, which is 196 milliamps, and then B is the negative of A. Here's the minus 1 times 196 milliamps, and this equation again is true for t greater than or equal to 0. And 5 time constants is again 2 milliseconds. Let's find the voltage across the motor. Back up here again. The voltage across the motor is going to be this node voltage minus this node voltage. So this node voltage is going to be equal to minus the current, I sub m, times the resistance of 0.2 plus 5. And then this node voltage here is going to be current in the inductor times 0.333. We're going to take the first one minus the second one. Go to the next page again. We've got 5 volts and then minus these two resistances with the current that's flowing through them. And that's going to be the expression we had just derived for the inductor current. Multiplying this out, we get 0.1045, and then our exponential equation. This is a small number, and we're going to subtract it from 5, and this is of course going to go to 0 very quickly. The voltage across the motor is approximately 5 volts. The motor is going to turn. The voltage across is fairly constant, and the motor is now spinning in the opposite direction. We're next going to open switch S2, which was closed before, and keep S1 still open once we get to 60 seconds. Our time constant's approximately 400 microseconds. 5 times that is much, much less than this, so we're going to reach that steady state value of 196 milliamps. Now let me do all this stuff on the drawing, as I did before. I have a current flowing in here of 196 milliamps, just as I change the state of one of the switches. With the switch open here, again, I've got no voltage here because I've got no path for currents. This one is cut off. And likewise here, I've got the switch open, so there's no current in here, so 0 volts, so this is also cut off. And the only path for current I could find is coming through here, going through here, back to the power supply back this way. Let's see if that guess again still works. If current were to flow through this bulk to drain diode, this node voltage would be minus 0.7. And that's hooked up here. This node voltage is 5, and this is equal to minus 0.7. Get 5.7 volts here. This is either going to be in the ohmic region or the current saturation. Again, let's guess that it's ohmic. We've got a low resistance. The voltage across here is pretty small. We say it's roughly 0. Now let's calculate the voltage here. It's going to be 5 volts, and then this terminal over here is hooked up here, and the voltage across here is approximately 0. This node voltage is going to be equal to 0 plus 5. 5 minus 5 is going to be 0. It's going to also cut off this transistor and have no current flowing. The pure only path for current I've got is to go through here, back through here, back through here, back to ground, and back up to that diode. We only have transistor 1 in the ohmic region. Let's use our equation with the source to gate voltage, because this is a p-channel device. 5.7 volts, K was 1.25, and threshold was 3, and that gives us 0.148. And our equation for the current in our coil is going to be starting at 60 seconds, some new A plus B times e to the minus quantity t minus 60 over tau. What's the resistance seen by the inductance? Let's just go back to the previous page. We're going to be looking back in here. All the independent sources set equal to 0. This is a battery of 0.7, shorting this to ground. And looking in here, I see 25 ohms, plus I see this resistance, which was 0.148, and then a short back to ground. So that gives me 25.148 ohms, or about 400 microseconds. Our current in the coil was 196 milliamps just before we switched, and then must be the same thereafter, and so that's going to be A plus B times e to the 0, or just A plus B. And as t approaches infinity, the circuit doesn't know something's going to happen. Simply going to find the current when this is a short circuit. The current in here is going to be the voltage across the resistances that we have divided by the resistance. So node voltage is equal to minus 0.7. It's a short here. And then this node voltage over here is 5 volts. I've got minus 0.7 minus 5 divided by the total resistance of 25 plus 0.148. I'm going to get a negative 227 milliamps with that calculation. That's going to be A plus B times e to the minus infinity, or just A. B is equal to 196 minus A, which was in minus numbers, plus 227 milli. Get 423 milliamps. My equation becomes A plus B times e to the minus t minus 60 seconds over tau, and that equation is valid for t greater than 60 seconds. But eventually the motor is going to shut off. Let me go back and just show you that. We have current flowing in this direction, but if current tries to change direction, it can go through this resistance through here, but then now I've got an open circuit in both these things. Current can't go this way. The motor just shuts off. Let's solve for how long it takes for the motor to shut off. You can set the current in the coil equal to 0, and that's going to occur at some time t1. We'll evaluate this equation at time t1. Bring this on the other side of the equation, then divide this over here, and bring this on the other side to get an exponential with a plus sign. Take the natural log of both sides. I just get the argument, natural log of 1.86, and cross multiply by the 398 micro. And we get that the difference of t1 and 60 seconds is 247 microseconds. This equation for the current in the motor now going in the opposite direction is between 60 seconds and 60 seconds plus 247 microseconds. The voltage across the motor we can also calculate, going to the previous page. This is the voltage across here. It's going to be this node voltage, which is minus 0.7, minus this node voltage, which is equal to the drop across the transistor, which is 0.148 ohms, times the current I sub m, and then plus 5 volts. That's what the equation is at the bottom of this page. This is a pretty small number, so it's roughly minus 5.7. Our motor has flipped its direction of voltage because now it's discharging its stored energy. It's actually generating power while this is occurring. It's again pretty short, but it is now dumping that energy. And then once you get greater than 60 plus 247 microseconds, everything goes to 0. And it's supplemental problem 413.